Good morning, everyone. Did you have a good time at the party last night? Super. Are you all awake from the party? Great. So let us start planning for goal. Remember, this is a level 300 session. So we would need you to have some amount of knowledge on simple storage service, Redshift, Kinesis, and Elastic MapReduce. As an individual, probably you are generating reams of unstructured data as we are talking now. Your mobile phones are generating data. And if this data is harnessed, you would be able to derive a lot of information from this data, which will help you to understand your customers and business better. The unstructured data is a maze, and in this session, we are going to show you how you can collect, store, and analyze this data at scale to get a 360-degree business view of your customers and your business. The cost of data generation is falling every day. Your watches, mobile phones, automobiles, and even heavy-duty machines are generating data. The global data is supposedly going to cross 40 zettabytes by 2020. And 85% of this data is going to be unstructured data. So what is unstructured data? Unstructured data is data that doesn't conform to any data model. Examples include personal messaging, business documents, web documents, and sensor outputs. All your phones are generating data today, and you are sending them to the cloud somewhere so that somebody can process it. And that data is unstructured data. Object metadata or markup does not alone give structure to the data. It doesn't give structure to the data. For example, HTML has markup information on it. This markup information does not give you structure, and it only provides you a means of getting relevant information from the data. You still need to classify it as unstructured data, process it, and create structure on it. There are 4 V's of the unstructured data: volume, variety, variability, and velocity. 90% of the world's data has been generated in the last 2 years, and this velocity is going to increase in the future. The 4 V's of unstructured data poses many challenges where you need to innovate to get some information from the data. The variety of data makes sure that one-size-fits-all solutions don't anymore work for you. You need to innovate on how you collect, store, and analyze data for various data streams. And each data stream is going to be unique for you in how you're going to collect the data or store or analyze the data. The amount of data that you need to store for pre and post processing is going to be huge. And the volume of data brings in innovation on how you're going to store this data. As I mentioned earlier, your velocity of data is always increasing, and this needs a scalable solution where you can sync all your events in. Why do you need it to be scalable? Because the velocity is not constant. It's going to increase with time or decrease. So maybe for reinvent, we had 1 million tweets coming in with the hashtag reinvent. Tomorrow I'll not have those tweets. So I need to have a scalable solution that can go up or down as needed. I then have variability of data. So the variability brings in the other 3 V's, or making it variable. You're making the other 3 V's variable, and you need a solution that can scale up or down based on that. And AWS provides you ways and means to harness this data at scale at a very low cost. Data generated from social media, from IoT devices, or your web page events needs to be stored in a high throughput sync store, and that can be Kinesis. Amazon Kinesis is a real-time streaming and processing service that allows you to store data at a very high velocity for up to 24 hours for you to process later. Data stored in Kinesis can be processed using applications running on EC2. These applications can scale up or down based on the amount of data present in Kinesis. The data in Kinesis is processed or pre-processed, I would say, pre-processed or massaged using these Kinesis applications. This application, if written on Java or Python, can you make use of Kinesis client libraries to further interact with Kinesis in real time. Data stored in Kinesis can also be processed using Elastic MapReduce. Elastic MapReduce is our service that allows you to run scalable compute, distributed scalable compute at scale. This data can be stored in S3 for further processing. You can also take data from web pages using applications running on EC2. These applications again can scale up or down based on the number of web pages I need to visit to extract information. I can use spot instances or on-demand instances here, which gives me the ability to scale up or down at a very low cost. The data collected from web pages is stored in S3 as unstructured data and further processed using EMR and again stored back into S3. So now we look at it, you have got enrichment happening at various stages for the unstructured data, and this enrichment gives structure to your data. And you will also notice that all data is being stored in S3. S3 is my data repository. I store my unstructured and my structured data in S3. So what is structured data? Structured data is data that resides in a database, conforms to a data model, maybe resides in fields in a file as well, but it conforms to a data model. And unlike unstructured data, structured data is generated by missions or applications. An example is unstructured data to structured data conversion. So this data is generated by missions or your order entry system, for an example. Structured data still exhibit the 4 V's. They still exhibit the 4 V's. You need a scalable solution to store and analyze this data as well. Apart from this, it also exhibits a management overhead of managing a database where you will store this data. You need to manage the database. You need to performance tune the database. You need to back up that database. Amazon's relational database service, DynamoDB, and Redshift allows you to concentrate on your business without having to do undifferentiated heavy lifting of managing the database. These managed services allows you to run your database at scale. So let us, continuing on the slide where I left on massaging the unstructured data. The data that is massaged by Kinesis applications can be stored in DynamoDB for further processing or can be used for millisecond responses to your real-time dashboards. Data stored in S3 can be loaded into Redshift, which is a petabyte scale data warehouse, which allows you to analyze the data using popular BI tools like JasperSoft, MicroStrategy, etc. At this time, I would like to invite Krishnan Venkata from Latent View on stage to talk about how they built a highly scalable application using the AWS building blocks to pan for gold for their customer. Krishnan.
Thank you, AWS, for this opportunity, and thanks, Ganesh, for giving the introduction to this session. Before we quickly go on to how we panned for insights from unstructured data. Let me talk to you about latent view analytics. I'm the director for West Coast region for latent view analytics. We are a leading and one of the fastest growing analytics service provider for Fortune 500 firms. We are an AWS advanced consulting partner. We are over 500 people strong, and we have over 50 people trained in AWS. In fact, Deloitte has recognized us as the top 50 India company, the fastest top 50 India technology firms to look out for. So before we go into how we panned for gold in unstructured data, I just want us to go back in history in terms of how an online user was typically understood. In past, typically when you wanted to understand online user behavior, you had two sources of data. You basically had structured and unstructured data sources from internal data. You had customer profile, typical transaction characteristics about what the person is doing with your website, etc. And you had some unstructured data, which is surveys, customer reviews, some of the support-related conversations he is having. And all of this is in there in server logs. But increasingly, we are finding out that this is just a one-way transaction of a user with a company. And that's not always the only version of truth. So we feel that there is some missing part here, and some of our clients have come to us and have asked us to identify what is this missing part that we can potentially use to augment and enable them to do better. I mean, to understand the customer better. And the idea where we started doing some of these projects is, and where we built a solution called Panel Miner, was to build a 360-degree view of the customer, where we not only had internal data as we typically had, but we also have external data. What customers are talking on in social media, what they are doing for, what is the kind of browsing history that they're having on their mobile phones, on their on different sites, on their web pages, etc. So this is not only interaction with your firm's online presence, but also your competitors, etc. So now you have not only data of interactions with your firm, but you also have external data. What I mean is a complete view of what the user is looking for, what the user is actually doing in the marketplace. But now that comes with a lot of challenges. One of the typical challenges is you have a ton of more data to analyze. So you now not only have your internal data, but you also have external data. And that brings a lot of issues in terms of handling this, in terms of infrastructure provisioning, management, and so it increases capital costs astronomically for clients. We also notice that there are ever shortening SLA time constraints. So clients typically want analysis to be done very quickly. Sometimes they want it real time, sometimes they want it to be done very quickly. And just because your data is increasing doesn't mean that your clients are ready to wait for answers. They actually want answers faster and quicker. In some of our clients' cases, we found out that almost 1 terabyte of data was being created from external sources which they were plowing down. And this was just with a panel of about 90 to 100,000 users, which was fairly dramatic. And there was also diverse data sources. So there is data that is done on web pages, mobile, on your Safari browsers, different kind of browsers. And you have also social data that is being there, which is being aggregated along with internal data. So you have multiple sources to go. So there's a new business challenge that is there. And you need to find out resources who are able to analyze all of this data and who have the technology experience and also the analytics capability to do all of this. So when we initially did what we did was we did a proof of concept in terms of looking at, can we create a 360-degree view of a customer? And like any other company, we started with a small pilot. We did this at a small scale. We did this with a couple of servers where we had about 24 GB RAM. We had 16 CPUs. I think it's about 5 terabytes of storage, etc. And we noticed that once we wanted to scale that, I don't think we would have been able to use just server infrastructure to do this, and we had to identify a cloud solution for this whole thing. And we actually benchmarked and looked at multiple ways we could do this, and we narrowed down on AWS. And why we chose AWS? I think the first important thing for our clients was there is no upfront capital expenditure. You only pay for what you analyze. So depending on the amount of data that you want to analyze, as much as the data is coming, You only pay for that. You don't buy all the equipment for all the data and keep them idle. Whenever you need equipment to be provisioned, you provision it. It's almost like a pay-as-you-go model, so to say. We were also able to scale. One of the things with our EMR solution, we were able to scale, almost take advantage of infinite scaling so that we could shorten our lead time to deliver. So we actually almost did it constant time, which I'll be covering later in the slide. And we also found out that, interestingly, the total cost of ownership was much lower than going for an in-house solution, which was very good. And the adoption was very easy. The greatest part about the AWS system is the strong support and auxiliary product services that are there. You have different kind of services that are available, so you can easily architect a solution and build it out. And it helps people who are just adopting cloud solutions. It helps them to move to AWS very quickly. And so this was almost a no-brainer for us to use AWS for a solution where we wanted to pan for unstructured data. So what I'll do in the next few slides is I will try to go through some of the challenges that we encountered as we were analyzing some of this unstructured data and how we overcame it, which will give you food for thought in terms of when you are looking for unstructured data analysis, some of these things, and you're looking at AWS as a solution for enabling this for your customers, you're able to understand what are the challenges we came up and hopefully would not make those same mistakes, so to say. The first challenge that we had when we looked at the user behavior was users are now continuously working on multiple devices. I think Ganesh mentioned that now people are interacting with their businesses through mobiles, PCs, tablets, and we needed to analyze the behavior across multiple devices. And there's different types of data that is being created. So one of the types of data is browsing history, which you're doing on your web pages. So you create your user profiles, you have HTML sessions that you have. There is also location devices. You're going through multiple places. And you also create a lot of data around in social, your Facebook feeds, your Twitter feeds, etc. So there's a ton of data that you're creating in addition to what you do, which is a transaction with a company. And there's also surveys and reviews, data that you typically, either at the end of a transaction or typically if you're part of a panel and you do surveys, those are data that you would typically have. And the method of collection for all of these sources are different. So typically for social sources, we used to write typical APIs. So Twitter gives you APIs, Facebook gives you APIs to be able to collect some of this data. And for the second block, we used third-party data providers who used cookies to actually be able to collect this data and provide it to us on a batch mode. The other challenge that we found out was that there were multiple velocities in which the data was coming. So some of the browsing history that was being made available to us was not in real time. So we went with the panel provider who used to aggregate this data and give us weekly batches of data. Whereas social data came to us as a streaming data flow. And people wanted to have real-time visualization of what is the sentiment about the brand as compared to its competitors, etc. In fact, we had a demo also that was set up in our booth, which talked about how we were doing the real-time streaming part. But they also wanted to integrate this with batch data that was coming from the panel. So one of the things that we had to do was what we call create a unit worker. The problem of creating, you've got a HTML data page, you need to create it into a structured data set for any analysis. You need to identify what do people view, what do people click, and what do they do on your online presence as compared to your competitors. And for that, just having raw HTML dumps is not going to be helping. So first, what we had to do was we wrote a Python unit worker, almost a unit cell, which showed us how to convert the unstructured data into a structured data set. Once you do this, how do you do this for 1 million files? You have got a ton of browsing history. Now you need to convert all of this unstructured HTML files into structured data, and we used Amazon EMR for that. And once you have converted it and written it into your S3 buckets, you need to load it into a data warehouse, and we used Redshift for this because Redshift was able to do very quick processing, and I'll talk to you about some of the processing speeds that we were able to achieve using Redshift. The other challenge that we got, as I mentioned and I alluded to it earlier, was we used to get a week's worth of browsing history on the users bundled into tar.gz files for every single day. So you'll have, for a week's worth of data, you'll have 7 such files. And they used to be dumped into an Amazon S3 location where they're typically, these files used to be about 10 GB, and once you uncompress them, they used to be about 50 to 100 GB, depending on the data that they have. And this had the user demography, the contents, the HTML pages that the person has browsed, what places has he clicked on, which is very useful information to say what is the user looking at and what is the user then responding to that. So it's not enough to show the coolest things unless the user doesn't do an action on top of that. So we needed to download all of these files, extract them, clean and upload them back. So this was a parallel processing architecture, and we are actually now encapsulating this, and hopefully we'll be moving this to the marketplace as well, where we have a base EC2 node, which the moment data is written, it used to poll the S3 buckets of the provider and say when they have dropped in data. And once data has been dropped, the EC2 node will send job messages using Amazon SQS, and it will store these job messages in terms of how to read these files and what needs to be done. The base EC2 node will also launch instances. So it will launch 7 instances, and each of these instances would then independently pull the jobs from the queue. And the jobs would basically tell that take each of those tar files, unzip, untar them, and basically process them, write those outputs into the S3 output buckets, and then destroy yourself. Now, there were multiple ways that we could have done this. We could have actually had this as just cloned instances, but we actually chose to have them as plain vanilla instances where these machines will be bootstrapped up. We used to take the code, we used to put the code here, and we used to actually run them, and we found that much more flexible in our architecture when we wanted to make code changes, we wanted to be, and in some cases where you have, say, multiple modeling techniques run, you would want each of these instances to operate differently also. So they necessarily need not be evenly balanced. In this case it was, but it is possible that some instances will work faster than other. The important thing here to note is that there is, once these instances are launched, they are on their own. They don't have to have any interaction with the base EC2 node. So for example, if the base EC2 node goes down, we don't lose this entire processing. We just lose some of the logs or some of the statistics that will be there in terms of the processing, but we don't lose the work. All of these instances can independently run, and they will write to the output. In case one of the instances fails, we keep having the alarms and notifications to actually basically keep looking at the SQS keeps looking at whether all of the jobs are being done, and the job is not removed till there is a successful complete message that goes back. So at the end of this, what we would have is, now that we have got this panel provider has given us data for a week, we have now got in the output up to 1 million HTML files that are ready to be processed by our process. But this architecture was important because we needed to do this on a fairly quick time. We are actually looking at ways by which we can, instead of having this as a single tar.gz file for every day, we could have it for a day cross hour. So now you have 168 instances that you can potentially have. You don't have to just do it as 7 days. So there are ways to optimize for this as well to increase the extraction process. But this is how we were able to do it, and these are S3 buckets. And now the HTML files can be consumed by a process in terms of how you can convert it into structured data. So now that we've got all the HTML files, the next challenge is, okay, the HTML files are great, but how do you convert them to structured data? And you needed to move the HTML file into a structured data set around different features, different elements of the HTML things which are important for the client. So we used a tree-based comparison logic to extract features from the HTML. So we identified that typically in a tree traversal logic, you will have, you'll start with a head, and you'll start with the HTML head, and you'll have the div classes, etc. And as the Python worker would go here, there would be a rules engine that we have written saying that this means that if once you have gone to this side, this means that you have identified feature 1. Please extract this information and put it into a table. And we would then go across this and we will read that entire HTML. It's almost like a tree traversal logic. And so there were 3 layers that are, or 3 levers. One is the HTML data that is there. There is the parser which actually parses through the entire HTML structure, and once it identifies a certain path, it goes and checks for the rules engine to see whether this rule has been configured. Now there are some interesting scenarios here. Web pages are not constant. People introduce new features, right? So you have new things that are constantly being introduced. So this rules engine is your key to be continuously updated. So your rules need to be continuously updated. So we used to update it on almost a weekly basis, in which we update rules for the new features that typically happen. And we also identify which rules are no more this one. So for example, if your competitor is changing certain features, he could change it either at the level, at the div level, he changes the entire feature, or he introduces a new div class, etc. You will be now able to identify which kind of new features are being launched. You can also identify among those features what has been the user engagement. So great that he has launched a new feature, a lot of users have seen it, but there's not enough coverage or there is not enough engagement. So this was extremely useful to start analyzing new feature introduction into the users. How many of them are looking at it? What is their response rates? And this kind of data was not available to our clients at all. So we used to extract all visible features. I mean, invisible features are not really required because those are not things that the user is seeing. So we only extracted visible features, and also the layout and position of each feature, which is very critical to identify which are those parts in a web page that people are actually recognizing. So is the F kind of heat map still existent on, is there a different kind of heat map on your web page because of your web design? These are all inputs that can potentially be got from this analysis. So I mean, a simple illustration of how this process would be is that all of the panel data in the web or the web logs would be the source of the data. We will also have social data, and these are unstructured data that is potentially there. You would have, this is the Python unit worker that does the tree traversal logic, and it reads the rules engine and it basically outputs a feature. Or it outputs tweets and whether the sentiment is positive or negative, etc. And so this data is now structured, which is great, but you needed to scale up processing. So the unique thing for us was that one of the things, or one of the curveballs that the client threw to us was, irrespective of the amount of data, you need to do this in constant time. Once you have reached this process, if I give you 1 million files, and in this case it was a few terabytes of data, so if it is tens of terabytes of data or hundreds of terabytes of data, you need to still constantly process this. And that became a unique challenge for us because we needed to scale based on the input load, and we had to use Amazon EMR for this, where we were able to scale our processing depending on what the input load was. And what we also needed to understand was how would we go with it. So should we go with on-demand or spot instances, or should we go with reserved instances? One of the things here was we actually had to do multiple iterations and looking at multiple variations of input load, availability of spot instances and on-demand. In some cases, we were fairly aggressive. We went from a 20% on-demand, 80% spot, and we realized that the reliability is a bit lower. So we are not sure whether we'll keep getting enough instances to do it. So we had a time-based SLA, and we had also cost-based metric that we wanted to be conscious of how much cost we were incurring. And after a lot of iterations, we were able to actually narrow down on the fact that a 66% on-demand and 33% spot instances worked for us to have a comfortable leeway to meet the SLAs that we had. And we ensured that we were having enough leeway, and we were also cost competitive. And when you have a large number of files, you had 1 million set of HTML files, you have to have a memory-intensive name node because there were so many. So when I talk about 1 million files, we also encountered what we call a small file problem, and we also had a huge name node which had to have the pointers in terms of if I run multiple processes that are processing these HTML files, you needed to have a name node which actually had the pointers to which are the different HTML files being processed under which units and what are the outputs being written. The small file problem is the Amazon EMR has a unique way of allocating memory. It allocates memory for a job, and when you have a million files to be processed, we were quickly running out of memory issues. So some EMR fine-tuning steps were done by us. The technical team actually went through, and we worked with Ganesh's team to actually go through some EMR fine-tuning processes by which we overcame this. We ensured that the instances that we were spinning off were persistent, and we also didn't allocate too much of memory. So we were able to solve some of this. But in case the small file problem is actually critical, because sometimes it brings down the entire cluster. It actually can bring down this cluster. So when in testing, we actually noticed that this is a fairly critical thing, that if you have a large number of files to be processed in Amazon EMR, you need to be careful in terms of whether you're going to have memory problems or not. We also had to have transparent reporting of usage and stats, which we used DynamoDB for. And we also had a unique case in which, since we had a million files which were on the date format, on the DDMMYYY format, we had an Amazon S3 race condition. And let me just talk to you a bit about that, which is typically when you have the DDMMYYY kind of format, when you write the output into S3, typically the first character is what is used as an entry point into the S3 buckets. And so what happened was, because say we had from 10th March to 17th March, that was the week of data that was available. We had just one entry point, that was 1, right? And this became an issue. We could have, the MM and YYY are not changing in our file format. So we are having an issue that we have just one entry point and we have a large number of files. So we are hitting a race condition scenario. So one of the things that we needed to do, and one of the things that are very critical here, is to have an hash key generator. We did a simple hash key generator where we actually took a standard date. We actually took January 1st, 2010 as the standard date. And any date file that you take, you look at the number of days since the start of the January 1st, 2010. So you took, say, today minus the number of days, you find out the number of days, and you did a modulo 35 operation on that. The modulo 35 operation will come out with what the day index will be. And now instead of having one day index, you could potentially have up to 35 day indexes, or 1 or 2 or 3, right? And we also then went, so we said, okay, we have 35 entry points, which is very good. We've said, let's do a second iteration in which we'll, once you have got into the day, you can also have other sub entry points, and we created the week index. So we did the same thing. We found out the number of days. We did a modulo 7, so we found out the week, and then we did a modulo 35 and found out a new index in terms of what is the week index also. So based on this, we were actually able to create a fairly large index format, but what you will interestingly note is that the first character was now 35 entry points. This actually helped us increase the number of entry points into the S3 output, and this was fairly critical. Because we were noticing that once we were able to process, we were not able to write the output correctly into the S3, which was pretty painful for us. So this hash key generation was fairly critical. Now once you've stored this data into S3 buckets, you kind of need to have a way of retrieval. So you need to have a reverse hash key generator. So anytime you want to say, I want to look at what is my user behavior on so-and-so date, you need to identify what the hash key was. So you needed to have that in your Redshift database or somewhere to basically programmatically tell that this is the place that you're trying to look for. I told you at some point of time in terms of, or sometime earlier, that irrespective of the number of files we needed to process in constant time, and this was actually achieved using the Amazon EMR. If you notice, initially we were, I would say, not very efficient. We were actually just learning the ropes. But from week 6 onwards, we pretty much have a flat line in terms of processing. And we were also able to start looking at ways by which we can optimize the costs. And in fact, from week 19, which was the 5th month after we started getting here, we found out various input sizes. And this was actually double the amount of input that we were getting earlier, but we were processing all of this in constant time. In fact, since then, I think this is now in week 100 or week 150, and we are still on constant time. So this is a fairly robust process. It's fairly well evolved. And we noticed that Amazon's reliability is extremely good as compared to some of the competitors that are out there. One of the unique challenges that we did was we took a lot of time into solving the problem of taking out the unstructured data from the HTML files, putting it, we've got the social data, etc. And when we loaded all of this data into Amazon Redshift, we were not thinking of what are the kind of questions that the business wants to solve. We were very looking at getting the data available. So what we noticed was we had another project where we wanted to optimize the Amazon Redshift performance. We were seeing that some of the queries were taking about 15 to 20 minutes, and then we sat with Ganesh's team and said, we really need to get this to a sub-minute query. That was one of the requirements or mandates from the client, that we cannot be sitting for 20 minutes in front of a console waiting for data to come out. So the first approach was seeing that whether we can denormalize tables. Let's not have too many joins that are there, which are fairly expensive operations, as you would all know. So we had to have highly denormalized tables. So we would trade off space to time. And then what we decided was we tried to see what are the kind of questions that we're looking, and can we set appropriate distribution keys and sort keys. So the distribution keys, what are the kind of joins that people are doing, what are the kind of characteristics that people are looking for. So am I looking for what is the page experience on iPad versus iPhone? That tells me that if I'm comparing between form factors is a critical key to have. Or if I'm not really looking at form factors, then I don't really need to keep that as a sort key. So how should I organize my data? So we took a set of business questions that are typically, or we did a poll of the business users and found out that there are typically a lot of certain keys which they are very commonly used. And we started saying, let's use them as the appropriate distribution and sort keys. And just by using them, we were able to improve the performance by 8x. What we also realized after doing this is that Redshift has also an ability to do compression of the data, and that actually improves it significantly. Just by using our existing and not changing any distribution or sort key, we could improve, just by using the compression technique, we could use it by 40x or 40 times. So in a combination, when we were able to do it, queries which were taking about 20 minutes came down to about 20 to 30 seconds. And that was really remarkable for them, that they were now multiple teams could actually access data, get queries, quick responses to their queries. The other thing that we noticed as we were doing this is there is some amount of maintenance that needs to be done on Redshift. We need to periodically do some kind of defragmentation of your, as you are actually moving data into Redshift, you typically create chunks or blocks, etc. So vacuum and analyze typally sees that all of this data is aggregated in the right form. So you're actually putting all of the data in a contiguous format. So that helps in actually querying, etc. So periodic execution of vacuum and analyze is actually, I would say, one of the things that a database administrator should constantly look at, and it should be part of your process in terms of maintaining a pipeline. And you can also scale up and scale down the data warehouse on demand. So obviously you can have more nodes spun up if you've got much more data, and as well as you can scale down the number of Redshift nodes that were there. Lastly, we had the challenge in terms of analyzing, as I talked about. So this is the panel data. We also had some of the social data that is coming, which needed to be analyzed real time. So customers wanted to definitely look at taking them along with the panel data, but they also wanted to understand some of the themes, etc. When campaigns are being launched, what are the top themes? So what is the sentiment of what consumers are talking about? So we used Amazon EC2 workers, scaled up Amazon EC2 workers, and then we also used a in-house sentiment algorithm and a lexical parser. And what this used to do was it used to give out the top themes that are occurring and what is the sentiment around this. And this used to compare with the top sentiments and themes of a competition. So when you do a launch, what is the theme and what is the sentiment around the launch? What are the key themes that, or key topics that people are talking about, etc. And there's also ability to do real-time visualization of this on a flowing data. So we actually had done this for reInvent. We had actually got the reInvent Twitter stream being done live in our booth as well. And what you can do is, once you have created this template, I will talk about the cloud deployment template in the next slide. The AWS toolkit for infrastructure and process, so this was some of the services that we used. We used the identity and access management for overall security and access. We used the CloudWatch to monitor the infrastructure, so how the cluster is doing. We had dynamic scaling in Amazon EMR, so we used auto scaling. We used for notifications, simple email services to say, this is for cost thresholds, this is for usage thresholds. We used to use this, and this was some notifications that we wanted to do to see whether we need to intervene. And also when processes get completed, when processing is completed, you wanted to use notification services for that. So if I look at the overall architecture of what we looked at, so we had all these devices that used to give us data, and we have an identity access manager that controls this entire cloud solution. We had 3 buckets, which was social data, social streaming data. We had the provider data. This was the panel data of the browsing history that people were having, and there was some internal client data that was there as well. The provider data, we had a parallel processing architecture to extract that data and put it into Amazon S3 buckets. These were the HTML files that are ready for processing. Then we used Amazon EMR with a 66% on-demand and 33% spot to actually write the output back into S3 buckets. For surveys and reviews, we used a similar thing to the social, where we used EC2 content crawlers, and we had lexical analyzers to actually identify top themes and sentiments of what people are talking about in the survey. This was the unstructured part in terms of comments that you're giving in survey, which we could also write into S3 buckets. And the social data was being streamed in real time. We had used Amazon Kinesis, and we had auto-scaling sentiment parser workers. As Ganesh alluded to it earlier, that depending on the amount of data, you needed to have multiple sentiment parser flows or lexical parser workers to actually process all of the social data and put it into the S3 buckets. Once you have created this infrastructure, what we used was AWS CloudFormation, because we needed to replicate this for different regions. And as you know, online companies would want to look at different regions from a security perspective. There are different things that they want to typically replicate. So we used this AWS CloudFormation to be able to create deployment templates of this architecture for multiple regions. So it could be scaled or deployed in multiple regions very quickly. All of these S3 outputs, as Ganesh also mentioned about, was written into Amazon Redshift, which was a unified data store. And we use this for a lot of reasons. One is it was in the AWS ecosystem. It was also much faster than a lot of other data stores that we looked at. And we used Amazon DynamoDB for operations tracking. A lot of this was one of the things that typically clients ask for is, it's great to know that the process ran successfully. What is the time? What is the cost? Transparent reporting. So we had all of this happening at real time. So nobody used to come out with a report, etc. This used to automatically be there. There used to be a visualization in terms, the visualization that you saw earlier in terms of constant time used to come out of the DynamoDB. And this Redshift database was then used for mining insights. So you could look at what kind of features are your competitors giving richer features on their page? Are they giving better user experience? Are users more engaged on them? Are they spending more time? And a lot of questions. Once this data was available, this was truly data that can be merged with internal data, which is any internal transaction behavior, and you have got now a 360-degree view of the customer, which was used a lot for a lot of product planning, marketing, customer retention-based initiatives. As I'm winding down, I would say that some of the key takeaways that I would say is, or the learnings that we had was, I would visualize the process and the problem workflow and map out the requirements and the services available. So what are we really looking to conquer? Are we looking for a way to, what kind of data? Are we looking at real time? Are we looking at batch? Identify your problem statement and then try to visualize the process workflow. And I think this is fairly critical in terms of architecting your solution. And very importantly, you should also estimate the amount of data flow that would typically be there. So it is easy to build a pilot to identify your solution, but also to identify what will be the amount of data flow that would be there. We actually encountered, as I talked to you about the race conditions, that was basically about not foreseeing those problems well enough. So I think one of the great things would be to see how your data would flow into your different buckets and how that would actually be used and consumed. I think Redshift is also one of those places where I think you should have a sound underlying model. You should understand why it has been architected in a certain way, why your distribution keys, sort keys, etc. are being used in a certain way. It's very good to work with the business in trying to understand what are the questions that they are looking for. And that's very powerful in terms of fine-tuning Redshift. And we should ensure alarms and monitors. I think this is very critical for any cloud-based deployment. When things are going great, it's always going great, but you could have that rare event when, say, your name node is going down and you need to very quickly restart the process, etc. We use alarms and monitors very, very effectively to be able to monitor each and every step of the process, whether everything worked right, look at statistics and see, okay, there were certain processes that failed, they restarted, etc. How do we make them more durable? Are there other fail-safe operations that we need to do? And one of the most important things is architect in a way that your infrastructure and process is scalable and repeatable. So when we created the Python unit worker, I think one of the key things that we learned is now that we have created the way to take unstructured data and create it into structured data, we needed to scale this process, scale this across regions, etc. So it's extremely important to architect a solution which is scalable and repeatable. Once we did this, some of the things that our clients had to mention about some of the work that we did was a lot of the business impact. In fact, this was, we took about 1/10 the cost, half the cost, and we were about 10 times as faster than a conventional setup. And the team size that we had deployed for a project like this was about, I think, 1/20th of the overall team that used to generate insights. And we were responsible for about 1/3 of the business impact that was there in this client's P&L. And a lot of the Redshift tuning also, a lot of the analysts were actually extremely happy by being able to do sub-minute queries. I think the fact that they were able to do very quick queries, analyze data very quickly, and that too terabytes of data was something that they had not seen even in their internal infrastructure, so that was pretty cool for them. And I think the business teams were very, the product planning, the marketing teams were very happy with the kind of insight that they were able to get about their customers. So now they had views about what the customer was doing, benchmarking them to competition, what they're doing, say for example, not only on their website, but also on other apps, other websites that the person is actually browsing, etc. And so one of the things that they took this was actually, this was one of the key inputs into product planning decisions that were typically done in the strategic roadmap and trying to see what drives user behavior, what are the things that could be done potentially. So hopefully you guys had some sense in terms of how we developed this solution, and I hope this session helped. We have a few flyers in terms of the panel miner solution that I just talked about, and hopefully my technical team will also be able to answer any other questions that you have specifically to the solution that we built. But thanks a lot for coming. Thanks for your time.